So let's get back to maths. So what we did last time, so Tuesday, was we introduced 3 or 4, however you want to count, spaces, fundamental subspaces of Rn associated with some matrix you're interested in. Okay, so if we've got an m by n matrix, then we introduce the row space, which is the span of all the rows, and the column space, which is the span of all the columns, and the null space, which is the set of all the homogeneous solutions. And the row space and the column space are obviously subspaces because they're the span of something. We proved that the null space was also a subspace. And the first thing that we showed was that a linear system, Ax equals b, is consistent if and only if b lives in the column space. So that's a statement telling you something about the column space. And then we started trying to think about the row space and the null space. And we got as far as showing that if you've got 2 matrices that are row equivalent, then their row spaces are equal. And we claim that their null spaces are actually equal. That's almost obvious, but I'll write down a couple of lines to justify that in a second. But this is good news because you can choose that U, the thing that's row equivalent to your A, you can choose that to be in reduced echelon form. And then working out what its row space and its null space looks like is much easier than working with A directly. Okay, so we know that the row space of A is the row space of U. I just want to prove B now, that the null space of A is the null space of U. But this really is true because if it wasn't true, we wouldn't use those row operations, right? Row equivalent means you can get from one to the other by doing row operations. The whole point of our row operations is that it doesn't change the set of solutions of a linear system. Right? So we wouldn't have chosen the row operations we did if Ax equals 0 and Ux equals 0 didn't have the same set of solutions. We've already argued that they do. Right? Provided they're row equivalent, they have to have the same set of solutions. And so the null space is just precisely that set of all solutions to the homogeneous equation, so the null spaces are equal. Okay, so there's not very much to that, or in a sense we've already proved this, just in different language. Okay, so let's look at some examples. All right, so let's take these, this pair of matrices. So we've got an A and we've got a U. And we're being asked to find bases for the row space of A and the null space of A. Okay? And the ingredient we've been given is that A is row equivalent to U, right? And U is nicer because it's in echelon form. We haven't bothered putting it in reduced echelon form, but it's in echelon form. So we can try and work out the row space of U and the null space of U, and then we immediately have the corresponding statements for the row space and null space of A. Okay, so to understand a vector space, particularly to understand a subspace of some vector space you already understand, right? We already understand Rn, but if we want to understand a subspace of Rn, what we really need to do is write down a basis for it, right? Because if you have a basis for the subspace, you know how to generate everybody in that subspace. So if you want to sort of characterize or classify some subspace, understand it, you need to find a basis. So that's what we're going to try and do. So we know that we don't actually have to work with A, we can work with U. But if you stare at the U, right, the row space of U is the span of its rows. Now obviously we don't need to include the row of zeros because that's not going to contribute anything to the span, and you also can't have an independent set that has a 0 vector in it because you can multiply the 0 vector by anything you like and you still have the 0 vector. But if you kick out the 0 row, then you can see, just by eyeballing it, that what you have left is an independent set. Because if you've got two vectors, they form an independent set if and only if neither of them is a scalar multiple of the other. Right? If you're just talking about two vectors. So that second row is not a scalar multiple of the first row, so they're independent. So we can see that the non-zero rows of U span the row space, well, obviously they span the row space of U because we don't need to include the zero vector, but the point is they're also independent. So if you want to see that precisely, we take a scalar multiple of the first one and a scalar multiple of the second one, set it equal to 0. And if you solve that, you immediately get that C1 and C2 have to be 0. Well, immediately after maybe a couple of lines of doodling. So the non-zero rows of U span the row space of U and they're independent, so they're a basis. All right, so you've got a basis for row U, but row U is row A, so you've got a basis for row A, okay? And this is completely general. We'll write this down as a theorem in a second, but it's completely general. If you want to find a basis for the row space of A, put it in echelon form, and then just grab all of the non-zero rows, right? Those non-zero rows have to span the row space of the echelon matrix. Turns out they're also independent, therefore they're a basis. And the row space of U is the same as the row space of A, so you get a basis for the row space of A. Okay? I'm not going to prove that the non-zero rows of U are always independent. We proved it in 2025. But so if you're curious, you can go and look at this week's workshop. But the general idea is just that if you're in echelon form, below every pivot you've got a bunch of zeros. And that's enough to guarantee that the non-zero rows are all independent of each other. Okay? So it's the echelon structure that forces these non-zero rows to be independent. Okay? Because below each pivot, it's the only entry in that well, all the entries below that guy have to be 0. Okay. So let's think about the null space now. So again, we don't need to think about the null space of A. We can think about the null space of U because they're equal. So we can just solve the find a basis for the null space of U by back substitution. Right? Because we're just trying to find, if we want to understand the null space of U, we want to understand the set of all homogeneous solutions for U. So we want to solve the equation Ux equals 0. U's already in echelon form, so you don't need to do any Gaussian elimination. So to get the general solution to U's homogeneous equation, you just do a bit of back substitution. And what have we got? This is a pivot. That's a pivot. So the free variables are going to be where?
Rows 2 and 4.
Columns. Yep. Right. So this guy has a free variable and this guy has a free variable because they don't have pivots. So the free variables x2, we call x2 alpha, say, and x4. And So they're free, so they can be any real numbers you like. And if you solve it, you get x equals alpha 1/2, 1, 0, 0, plus beta minus 2, 0, 2, 1. Okay? So you write down the general solution. It's going to have two free variables in it. I've just separated that solution into the bit that's multiplied by the first free variable and the bit that's multiplied by the second free variable. Okay? There's nothing that we couldn't have done in first year. And now, one thing that's clear now is that these two vectors span the null space, right? Because we've written an arbitrary thing in the null space, which is a general solution to the homogeneous equation. We've written it as a linear combination of these two guys. So we can immediately see that the null space of, well, A, but also, I guess, really U, but A is the same, is the span of these two vectors. And the claim now is that this is an independent set, so it's actually a basis. So we can verify just by brute force by doing the same thing that we did for the row space, which we all hopefully are comfortable with doing now. You take an arbitrary linear combination of these two vectors, set it equal to 0, see what choices of coefficients you can get away with. It turns out you can only use only the trivial choice works. So this set is independent. So it spans the null space of U. It's independent, so it's a basis for the null space of U. But the null space of U is just the null space of A. Okay, so we've got a basis for the null space of A, and how did we construct it? We wrote down the general solution to the homogeneous equation, right? We all know how to do that. You just separate that out into one vector that's multiplied by the first free variable, another vector that's multiplied by the second free variable, yada, yada, yada. We can always do that. And what we saw in this case, at least, is that if you pick off the vectors being multiplied by all of the free variables, you get a basis. Now, obviously, they span. The interesting fact is that they're always independent. The set is always independent. Now, that's not entirely obvious. In fact, it's not obvious, but it's true. It's a little bit of work to prove it. It's one of the starred questions on the problem set. It's not crazy difficult. So if you want to, I'd recommend working through that starred problem, and you can prove basically what part C of this theorem is stating, is that if you take the general solution to a homogeneous equation, factorize it so that you've got free variable times some vector plus next free variable times some other vector, blah, 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 blah. The vectors multiplying the free variables always form an independent set, and therefore always form a basis for the null space. Okay, so we've seen at least examples of how to construct bases for the row space and the null space. I haven't talked about the column space yet. It's the hardest of the three. But here's a theorem that tells us in general how to construct bases for these spaces. And again, if you want to understand, the whole point of this is that we want to understand these spaces, and the only way to understand a subspace is to write down a basis for it. Okay, so if you've got any matrix A and some matrix U that's row equivalent to it, and you know that it's in echelon form and it's got R pivots, so you don't have to take it all the way to reduced echelon form. Sometimes that's annoying, but you always can if you feel like it. Whatever you find convenient. A first claim is that a basis for the row space of A is a set of non-zero rows of U. So exactly what we saw in the last example. So the claim here is just that what we did in the last example always works. Okay, so this was, I'm not going to prove it here, but this is 2025 workshop. The second claim, which is, which is the hardest to prove, is that a basis for the column space of A is a set of pivot columns of A, right? So what's a pivot column? It's a column that ends up getting a pivot when you put it in echelon form. So the column, you've probably seen this before, hopefully, but the column space is a little bit more subtle because you don't pick the columns in the echelon form. You pick the columns in the original matrix that correspond to the columns in the echelon form that have pivots. Okay? So it's more complicated than the row space case because the column space of A is not equal to the column space of U. They are still sort of related, but they're not equal by any stretch. Okay. The third statement here is that, as we just saw in the last example, if you look at the homogeneous equation, which is, so the set of all the homogeneous solutions is the null space. If you do that, you're going to find n minus r free variables if r is the rank of A. And you can write the general solution in this form. Right? So this isn't actually anything new. We knew this just from solving linear systems. The new thing is that the set of these vectors multiplying the free variables, when you write out the general solution, those vectors form a basis for the null space. And the only caveat you need to be careful of here is you need R to be less than N, otherwise this set's empty. Right? Now why does that make sense? Why don't we really mind that this doesn't work when R is equal to N? Yeah, there's no free variables, right? So if R is equal to N, you're saying every column has a pivot in it. There's no free variables. So how many solutions to the homogeneous equation do we have? We just got one, right, which is the zero vector. And we know that the vector space that only has zero in it doesn't have a basis. So we don't need to go and find a basis in that case. There's nothing to do. So this works in every case where you actually need it to work. Okay. So I want to look at an example of this, but before I move on, is this kind of clear, at least what we're saying? So if you want to try and work through proofs of these, part B is I'm going to call a double starred problem. It's the hardest problem on all of the problem sets in this unit, but it's doable. You just have to be patient and have had enough coffee. This one is just sort of this one's far more doable. You shouldn't be scared of it, even though it's a bit of work. You can prove that. But again, it's starred, okay? So if you're 2021, these are just optional. All right. So let's do some examples. A basis for the column space in that example. So what was that example? Let's go back and have a look. All right, so we want a basis for the column space. We're going to use our theorem to find a basis for the column space. So the pivots in U are here and here. So we don't want those columns, we want these columns, right? So the first column of A is a pivot column because there's a pivot in its echelon form. The third column of A is a pivot column because there's a pivot in its echelon form. And so 2 minus 8, 4, 1 minus 6, 3 is a basis for the column space. Of A. So this is a basis for the column space of A. Okay, does that make sense? All right, let's look at another example, just to drum this in. So let's look at this matrix now. And we want to use the theorem to find bases for the row space, the column space, and the null space. So what do? You take it and you put it in echelon form. And pretty much whenever I actually ask one of these on an exam or something, I just tell you what an echelon form is, because I can't be bothered having to take half marks off for minus signs and stuff like that. So I just tell you what the echelon matrix is and then ask you to do something with it. So A is row equivalent to this thing. So these two rows give a basis for this row equivalent matrix and therefore the row space of A. So 1, minus 2, 1. 0, 0, 1, 2 is a basis for the row space of A. And I look at who has pivots. The first column has a pivot. The third column has a pivot. So the first and the third columns in A give a basis for the column space. So 1, minus 1, 2, and 101 is a basis for the column space. And now we just need to think about the null space. So we just find the general solution, right? So it's a really first year sort of problem. Just look at the homogeneous equation, find the general solution. All right, you do that just by back substitution. So again, just like the last example, the free variables are x2 and x4. No particular reason why that happened to be the case in both examples, except that I'm not very imaginative, I suppose, but it could be anything. But you write out the general solution, and you separate out one term for each free variable, which you can always do. And then you pick off the vectors multiplying the free variables, they're your basis. So 2, 1, 0, 0. 1, 0, minus 2, 1 is a basis for the rows, for the null space. Okay, so there's no new ingredients in finding these bases. All you need to know how to do is Gaussian elimination. So you get the echelon form. Once you get the echelon form, you get bases for the row space and the column space. And back substitution, that gives you the basis for the null space. Okay? So there's no new tricky methods. It's just sort of a different interpretation of stuff that we're already doing with linear systems. Okay. Is everybody happy how to find bases for these three spaces? All right. So what can you do with these bases? Well, you can actually do a lot of things. But here are a number of, well, just below is a number of important consequences of the fact that we know how to construct these bases. But I need to start with a few definitions. And actually, the first thing I want to mention is the following remark, that the number of pivots doesn't depend on the particular choice of the echelon form of U, right? So we hadn't actually observed that before. We sort of knew in practice that always held. But the number of pivots is precisely, say, the dimension of the row space. you can't get two different notions of the dimension of the row space from two different echelon matrices, right? So this theorem is telling you that no matter which echelon matrix you pick, you get a basis. We know that the number of things in a basis has to always be the same for any basis, any pair of bases in the same space. So the uniqueness of the cardinality of bases tells us that no matter which echelon form you look at, you can have the same rank. Okay? So this vector space structure, machinery that we've built up, proves something that we sort of stated a long time ago but didn't actually prove. We all sort of believe, but here's one way of understanding why it has to be true, right? It's because of how we know how to find bases for these spaces like the row space or the column space. And because we know bases for a given space always have the same number of things in them. Okay. So this number of pivots is obviously important because it gives the dimension of the row space and the dimension of the column space, right? That's another observation. You'll notice here that in each case, when we write down a basis for the row space or a basis for the column space, we get as many things in our bases as we have pivots, right? Because in the row space case, it's all the non-zero rows. They're the rows that have pivots. In the column space case, it's explicitly all the columns that end up having pivots, okay? So this number of pivots is a very important number characterizing our matrix, and we therefore give it a name. We call it the rank. The sort of complement to that is a thing that we call the nullity. So n minus the rank is the nullity. What's n? N's the number of columns. So the nullity is, if we go back and look up here, the nullity is precisely the number of things in the basis for the null space. Okay, so the nullity is the dimension of the null space, the number of things in a basis for the null space. So the rank is the dimension of the row space and the column space. The nullity is the dimension of the null space. Okay, so the nullity is counting how many free variables you have in the homogeneous solution, and the rank is counting how many leading variables you have, right? So nullity is how many free variables, rank is how many leading variables when you're trying to solve the homogeneous equation. Okay, just as a bit of jargon, which is essentially unavoidable, I mentioned Tuesday that there's this fourth space that's really important, which is the null space of the transpose. So we're going to give that a name. We're going to call that the co-kernel. So we'll call the null space the kernel and the null space of the transpose the co-kernel. And we'll see that they play, we're going to see various explanations for how these spaces fit together and tell us stuff as we progress through the next 6 weeks. But we'll see that these sort of play symmetric roles in some sense. Okay. But now let's sort of summarize all of this stuff that we've just convinced ourselves of about the dimensions of these spaces. And this is sufficiently important, these observations, that it gets called the fundamental theorem of linear algebra. So the fundamental theorem tells us the dimensions of these four spaces. Okay? So the dimension of the row space is the rank, the dimension of the column space is the rank, the dimension of the kernel is the nullity, the dimension of the co-kernel is, I don't know, some kind of co-nullity. Right? It's not the number of columns minus the rank, it's the number of rows minus the rank. So we've already proved 1, 2, and 3 because we've explicitly constructed bases for each of these spaces. And their dimensions turned out to be precisely these numbers. Okay, so we don't have to do anything for 1, 2, and 3. They follow from our basis theorem. And we get 4 just by considering transposes, right? So let's let B be A transpose. Now, B is just some matrix. So the rank of B is, from our theorem, the dimension of the column space of B. But what's the column space of B in terms of A? What space associated with A is the column space of B? So what's space? I've got the column space of B, yep. It's the row space, right? Because the columns of B are precisely the rows of A. So if you look at the span of the columns of B, you're looking at the span of the rows of A. So the dimension of the column space of B is the dimension of the row space of A, because column space of B is the row space of A. And our theorem tells us that sorry, not that one, this one, tells us the dimension of the row space of A is the rank of A. Which is R, the number of pivots. And so now we just use part C. So we've used part, sorry, not part C. We've used part 1 and part 2. Now we're going to use part 3, but applied to B. So 4, 5, 9C implies that the dimension of the null space of B is just m minus the number of pivots. Okay? And so one consequence of this, which is really not obvious at all, is that the rank of A is equal to the rank of A transpose. Right? So the number of independent columns is the same as the number of independent rows. This vector space machinery tells us that. It's not at all clear if you're just sitting there thinking about linear systems with no extra machinery why this should be true. Okay. So find the rank and the nullity of the matrix in A that we were just looking at. So in our example. So we had 2 pivots, so the rank was 2. And we had 2 free variables, so the nullity is also 2. Right? So this 4 minus 2 is number of columns minus number of pivots, or number of columns minus the rank. That's the number of free variables, that's the nullity, which is 2. Okay? In general, these two numbers are not going to be equal. For this particular case, they happen to be. Okay, so let's do a poll. So let's consider some linear system, AX equals B, and say that we've got 20 equations and 24 unknowns. And let's say that when you go and solve the homogeneous equation for this thing, you find that there's your null space is spanned by 4 independent vectors. So can we be certain that the system is consistent for any choice of B? That's the question, right? Given this information, that how many equations you have, how many variables you have, and what the size of the null space is, do you know whether or not that system is always consistent? So is it guaranteed that the system has to be consistent for any B? Is this enough data to work that out? Let's just try and summarize what we've got. So A sum n by n matrix. X is going to live in Rn. B is going to live in Rm. Right, that's always what you get if you look at an n by n linear system. Now in our case, right, the number of equations is always the number of rows. The number of equations is 20. So we're looking at a m equals 20 row matrix. And the number of variables, which is the number of columns of A, is 24. And we can now, because we know the nulls, we know how many independent vectors span the null space. That's saying that we have a basis for the null space, right? So the basis for a basis for the null space has 4 things in it. So the dimension of the null space is 4. That's what that sentence is really, or that statement is telling you. So the dimension of the null space of A, which is just the nullity by definition, is 4. Now, the fundamental theorem tells us the nullity is n minus the rank. Right? So we know n, that's 24. So we can now work out the rank. So the rank is 20. Okay, so now, do we think the system's always consistent, now that we know the rank's 20? Okay, so just knowing the size of your matrix and the nullity is enough to tell you the rank. What can we tell from the rank? Well, the rank tells us the dimension of the row space and the column space. So the dimension of the column space is 20. And you'll notice 20 happens to be m. So what have we got? Now what space is the column space a subspace of? The column space is a subspace of Rm, right? Because you've got n vectors, they all have length m. So the column space is some subspace of Rm. And we've just worked out that the dimension of that space is m. So what does the column space equal? You've got a 20-dimensional subspace of a 20-dimensional space. What do you know? Yeah, right? The only 20-dimensional subspace of a 20-dimensional space is the entire space. There aren't any 20-dimensional proper subspaces of a 20-dimensional space. So just by knowing the dimension of the column space and knowing that it's equal to the space that it lives in, so knowing one number about this space is enough to tell you that the space is Rm. Okay? Now, what does that mean? That means that no matter what B you choose, it lives in the column space. Right? Because all the B's that we're interested in this linear system live in Rm. But Rm is the column space of A. So no matter what B I choose for my linear system, it lives in the column space. So what do I know? It's consistent, right? So we showed on Tuesday that a linear system AX equals B is consistent if and only if the right-hand side lives in the column space. So if you know the column space is Rm, you know the system's always consistent. All right, because everything lives in the column space. There's nothing that doesn't live in the column space. So this is another way of summarizing whether or not a linear system is consistent. You just ask the question, is the column space all of Rm? Okay, so the answer to that one is yes. All right, any questions about that one? Okay. All right, so we can add to our list of equivalent statements. So where did we get up to? So there's your equivalent statements for invertibility. These ones we already have, so I'm not going to write out a proof for this because the last few are sort of almost you get for free once you understand the fundamental theorem. So we already had those ones. Now, I will just point out that this one, the statement that the homogeneous solution only has the trivial solution, that is equivalent to saying the nullity is equal to what? 0. Right? So part B that we already had, if you write it in fancy language, it's precisely the statement that the nullity is 0. Right? Which is this one. Right? So B immediately implies O. The fundamental theorem tells us that the sum of the rank and the nullity equals n. Right? So if the nullity is 0, the rank has to be n. So O immediately implies A by the fundamental theorem. And once you know the rank, these ones follow for free. Okay, so the rank is telling you how many pivots you have, and you immediately see that because you've got a maximal number of pivots, every column's got a pivot, every row has a pivot. So the rows form an independent set and the columns form an independent set. You've got n of them, so you've got independent sets in Rn, so they have to be bases for Rn. Right? Remember that if you're in an n-dimensional space and you have a set of n linearly independent vectors, that set is a basis. Okay? So as soon as you know that all of your columns have pivots, the columns are a basis for Rn. As soon as you know all of the rows have pivots, the rows form a basis for Rn. Okay? So all of these basically follow from fundamental theorem here and just this definition of nullity here. So we know lots of characterizations of invertibility now. Okay. So the next thing I want to talk about is really still following on in the same vein, right? So the motivation for the next thing I want to talk about is that we still want to understand the row space and the null space and the column space and the co-kernel. What we really want to do is understand how these spaces relate to each other. Okay? So we know that the null space and the row space are both subspaces of Rn. The only relationship that we've talked about so far between two vector spaces is subspace. Right? We've said, all right, we know how to define when one vector space is a subspace of another vector space. But we haven't talked about how to relate two subspaces of a bigger subspace, a bigger vector space. That's what we want to do now, right? Because we know the row space and the null space are subspaces of Rn, but how do they interact with each other? Right? What's their relationship? And likewise, what's the relationship between the column space and the co-kernel? Because they both live in Rm, right? They both live in the codomain of our linear transformation, our matrix transformation. The row space and the null space both live in the domain of our matrix transformation. So what's the relationship between them? So to understand that, I need a little bit of machinery. This machinery is sort of useful and interesting in its own right. So we'll define it in general, but I'm really going to apply it to this row space, null space type stuff. So if you've got two subspaces of a bigger vector space, we can add them together. Okay? So we can define what V plus W means, where V and W are both vector spaces, and it's just sort of the obvious thing. It's the set of all sums that you get by taking something in the first space and something in the second space and adding them together. Okay? So the sum of two vector spaces is a set of all sums you can make by taking one thing from the first space and one thing from the second space. Okay? Now, there's a nice property that the sum of two spaces may or may not have. Well, there's a nice property that two spaces may or may not have, and that's that they've got the smallest intersection possible, right? Now, you might ask, why can't two subspaces have an empty intersection? So why can't we have a smaller intersection than saying the zero vector? Why can't it be empty?
Because the null space has to be zero.
So it's not the null space that we're talking about here, but every vector space has to contain zero.
Yeah.
So you can't be a subspace unless you contain zero. So V's got to contain zero, and W's got to contain zero, otherwise they're not subspaces. And what we're saying here is that they don't have any other overlap. So they got the smallest overlap they could possibly have and still be subspaces. Now, so if V and W have this minimal possible intersection, then when we add them together, we draw this fancy plus sign, called O plus, and we say the sum is a direct sum. Okay? So even if V and W have some non-trivial intersection, you can still add them together, but then you don't use the O plus, you just write this. But in nice cases, V and W have this minimal possible intersection, and then when you write their sum, you call it a direct sum when you use O plus. Okay. Now, the first statement I want to make is that this sum of two vector spaces is itself a vector space. Okay, so V plus W is a subspace of U, regardless of whether it's a direct sum or not. It's always a subspace. The nice thing about direct sums compared with other sums is basically analogous to the nice thing about bases compared with spanning sets, right? So if you've got a basis, there's only one way of writing everybody in your space in terms of linear combinations of the basis. But if you've just got a spanning set that's dependent, there's infinitely many ways of writing some vector as a linear combination of the things in your spanning set. The nice thing about a direct sum is that for every element of your sum, there's precisely one way to decompose it as a sum of something from V and something from W. Okay? So the sum is direct if and only if for every vector in the sum, there's a unique way of decomposing it in terms of something from the first space plus something from the second space. Now, the proof of this is kind of nice, and I don't want to rush it, so I'm going to do the proof of this after the break, but I do want to just introduce one more concept before we go, and that's that there's a really nice way, if you're in a space like Euclidean n space where you have say the dot product, and we'll generalize this later to abstract things called inner products, but let's focus on Euclidean space for the time being. So Euclidean space, it's a vector space, but it's also got this structure having a dot product. And then you know what being orthogonal means. If you're sitting in two subspaces of Euclidean space, if everybody in the first space is orthogonal to everybody in the second space, we say those spaces are orthogonal, and we write this. This is called V perp W, right? So V and W are perp. They're orthogonal to each other. The statement here says that if you've got two subspaces of Euclidean space that are orthogonal, then their intersection is 0. Okay? So this is a nice way, if you're in a nice space like Rn, Euclidean space that's got a dot product, some kind of inner product, it's a nice way of proving that a sum is direct, right? If your two spaces are orthogonal, there's no way they can have a non-trivial intersection. Okay? So this is an easy way of checking in practice that the sum of two spaces is a direct sum. You just show this. This is sufficient. It's not necessary, but it's sufficient in order for this intersection to be minimal. Okay. Now, the very last definition I want to leave you with for the breaks, because it relates to one of the problems on the problem set, is the notion of an orthogonal complement. So sitting in a Euclidean n space, the orthogonal complement of some subspace is the set of all vectors in Rn that are orthogonal to it. All right, orthogonal to every vector of W. Okay, so W perp, if W is a subspace